Hello viewers, so welcome back to the course on scientific computing in MATLAB. So today we will continue with the previous lecture on the cubic spline. So in the previous lecture we have found that how we have discussed that how we can find the cubic spline for a given interval, and then we have started with the expression that how we can express the cubic spline in each of the subinterval. And then in the end we came with the equation number 6. So that is the given polynomial, that is the cubic polynomial we are defining, and now we have to find out what is the value of this mk's, the second derivative in the for the given cubic value, cubic spline. So now we have to find these values. So let us continue with this one. Now, so from the 6, differentiate equation 6 with respect to x. So I will get sk dash x is equal to mk by 6 hk into 3 times to minus 1 plus mk plus 1 by 6 hk into 3 x minus x square. So this is all constant terms. So I will get only here minus yk over hk minus mk by 6, because this is the coefficient of x. So I will get minus 1, so that will be there, plus six. So that is the expression for this. So from here I will get that my s dash k can be written as, so it will cancel out, 3 will cancel out 2, so it will be minus mk by 2 hk, x k plus 1 minus x whole square. Similarly, plus mk plus 1 by 2 hk and then I will get this expression. So from here I can write this as a yk plus 1 minus yk by hk. So I can take this term common, and then this minus and this plus. So from here I can write minus mk plus 1 minus mk by 6. So this is my sk dash. So I call it equation number 7. So this is a function of x. Now I find out the value at xk. So what about at x is equal to xk? So sk dash at xk. So if I put xk here, so this will be xk plus 1 minus xk, so that will be hk. So I can write from here directly. So this will equal to mk by 2 hk, because hk will be square and this will cancel out. So this will be this value. Now from here this is the 0 value. So I will get from here, so I will get yk plus 1 minus yk by hk, and from here minus mk plus 1 by 6 plus mk by 6. So from here I can just take this value common, this will be also hk, this will be hk. Now from here I will get this into hk multiplied by hk, and now I can, so this will be into hk, and this is also hk. Now from here this will be equal to hk and that will be hk. So I can write this quantity together. So I can write this as a mk hk by 6 minus mk hk by 2 plus yk plus 1 minus yk by hk minus mk plus 1 hk by 6. So this quantity, so now I will get from this so this can be written as minus mk hk by 3. I am taking the LCM plus yk plus 1 minus yk by hk minus mk plus 1 hk by 6. So I will get sk dash xk. So this expression 7 is equal to 8. So the only thing is that we made the mistake here. So I will multiply by hk also, because this hk will cancel out. I will get the hk and hk. So I am writing hk here and continue with this hk, and in the end we will get this expression. Now we can rewrite equation 7 for k minus 1. As this is written for kth subinterval, we can write this as for the k minus 1 interval. So I can write this as a s dash k minus 1 x. This is equal to minus m k minus 1 by 2 h k minus 1 x k minus x whole square plus m k by 2 h k minus 1 x minus x k minus 1 whole square plus y k minus 1 by h k minus 1 minus m k minus 1 by 6 into h k minus 1. So this is I have written for the subinterval from k minus 1 to k. So suppose this is equal to 9. Now s dash k minus 1 at xk. So let us see what will happen in this case. So if I put xk, this will be 0. So this will be hk minus 1. So from here I can write this expression directly. So I will get my mk by 2 to hk minus 1 square. So this will cancel out. So I will get hk minus 1 plus this is yk minus 1 divided by hk minus 1 minus, so from here I will get mk hk minus 1 by 6 plus mk minus 1 hk minus 1 by 6. So this expression can be written as mk hk minus 1 and this term I can take together. So this is half minus 6. So this can be written as mk hk minus 1 by 3 plus mk minus 1 hk minus 1 by 6 plus yk minus 1 by hk minus 1. So that is s dash k minus 1 xk. Now I know that the derivative should be same. either moving from left or right. So, from here I will write it equation number 10. Now, since s dash k minus 1 at x k is equal to s dash k at x k. So, that is the condition that the function should be smooth enough. So, that gives me that m k h k minus 1 by 3 plus m k minus 1 h k minus 1 by 6 plus y k minus 1 over h k minus 1, that should be same as, so it should be equal to minus m k h k by 3, I am writing from here, plus y k plus 1 minus y k by h k minus m k plus 1 h k by 6. So, I will get this expression. So, we just write this expression as dk minus 1 and this is dk. So, from here I can write now we get. So, after doing the manipulation, what we will get is this one h k minus 1 m k minus 1, because from here I will get the LCM, that is 6 on the both side, and I will get this value. So, this is m k minus 1 into h k minus 1 plus 2 times h k minus 1 plus h k into m k. So, this is this and this value I am taking on the left side. So, this will be h k plus h k minus 1 by 2 times m k and plus this value will take on the right hand side. So, this will be equal to m k plus 1 h k, that is equal to 6 times dk minus 1. So, this is I can write, and this is true for all k from 1 to up to n minus 1. So, in the end I will get this expression where my m k is second derivative at x k. So, that we have defined. So, this is my m k. So, m k is the second derivative of a dash at x k. So, this is already defined. So, that is my expression and I call it 10, 11. Now, from here we will see that equation 11 gives us a system of linear equations. How? So, let us start with k is equal to 1. So, if I take k is equal to 1, it will be h 0 m 0 plus 2 times h 0 plus h 1 m 1 plus h 1 m 2, and that will be equal to 6 times d 1 minus d 0. So, this quantity is known to me. On the right hand side this quantity is known. Now, if I take k is equal to 2, I will get, so from here I will get h 1 m 1 plus 2 times h 1 plus h 2, and that is m 2 plus h 2 m 3 6 times d 2 minus d 1 and so on. So, in the end I will get n minus 1. So, I will get h n minus 2 m n minus 2 plus 2 times h n minus 2 plus h n minus 1 m at n minus 1 plus m at plus h n minus 2 m at n, that should be equal to 6 times d n minus 1 minus d n minus 2. If I write this expression in the matrix form, so we will get, I need to find m0 m1. So, I will get h0, then 2 times h0 plus h1 then h1, and all other terms are 0 0. Suppose here I write m0, m1, m2, and in the end I will get up to mn, and from here I will get 6 times. So, I can take 6 common d1 minus d0, d2 minus d1, and in the end I will get dn minus 1 minus dn minus 2. So, that is the first equation. The second equation is start from here. So, this will be h1 2 times h1 plus h2 and then h2. So, from here if you see h2 and this is the 2 times of this one, h1 h2, this is the 2 times of this one. So, in this way I can write that in the end I will get h n minus 2 times of h n minus 2. So, this is h n minus 2 will come here. So, this should be 1. So, this will be n minus 1. So, now from here if you see we will get this expression. So, we will get, so I suppose I call it this matrix A into M is equal to B. Now, this expression if you see, now the, so we have n minus 1 equations in n plus 1 unknowns, because I need to find this m0, m1 up to mn. So, this n plus 1 unknowns are there, and the total number of equations depends upon that how many condition we are, so that is n minus 1. So, we have n minus 1 equation in n plus 1 norms. So, this is a rectangle. So, from here I can say that A is not a square matrix. So, how I will to find this equation? So, that depends upon that the extra 2 conditions we have to add. So, from here I will now to solve, I call it now the matrix A is a tridiagonal matrix. So, this is a tridiagonal matrix basically. Now, we have to add 2 extra conditions to solve the system 12 . 12. So, we have to add 2 extra condition. So, this is the way we can define. So, this is called some extra condition. So, the case 1 we call it clamped cubic spline. So, clamped cubic spline means we define that our S dash at x naught, the left boundary condition at the left boundary, and S dash at x n are given. So, these values are given to us. That is called the clamped cubic spline, because the derivative is given. The value of the derivative at the extreme left and the extreme right, that is given to me. The second one is that natural spline, natural cubic spline. So, in the natural cubic spline we have the condition that S double dash at x naught is equal to. So, this is given that the curvature, the value of the curvature at the extreme left and the extreme right, it is 0. So, that is called the natural cubic spline. So, in this case, depending on that what condition we want to find, we can solve this system. So, let us take this one. So, we consider the case of natural cubic spline, which implies that S double dash x naught, that is my m naught, that is 0, and S dash at x n, that is my m n, so that is 0. Now, if I substitute these two values, so from above system we get, now if you see from here, this value is 0 and this value is 0. So, there is no need to write these values. So, if I multiply this y, so this m0 is multiplied by h0. So, I can remove this also. This mn is multiplied by this hn minus 1. So, I can remove this value. So, from here our system reduced to reduced system is given as. So, now we have reduced the system. So, if you see from here, I will get so the first one will start from 2h0, h0 plus h1, h1 0, so I can write it as a, starting from m1, m2 up to m n minus 1. The next one is the same, so it will be h1 and h2. So, this one will be h1 2 times h1 plus h2, h2 and so on. So, in the end we will get, so this part will be 0. So, this is 0, this is 0. So, I will left with this part only. So, I will get hn minus 2 and 2 times hn minus 2 plus hn minus 1. Because this is also, I will multiply by this factor. So, this part will be 0. So, I can remove this one and I will left with this one. So, now from here you can say that this is equal to the corresponding condition d1 minus d0, d2 minus d1, and in the end I will get dn minus 1 minus dn minus 2. So, it is 12, it is 13. Now, we have reduced system. So, this is my A n minus 1 cross n minus 1 now. Multiply with the vector m, that is n minus 1 cross 1, and it is equal to, I call it B, that is n minus 1 cross 1. So, this is now a system of linear equations, and also the matrix A is diagonal dominant. Why it is diagonal dominant? If you see from here that this is a sum of the previous one and the next one. So, it is definitely great, this value is greater than h1, this is greater than h1 and h2. So, I am taking the sum and 2 times of this one. The same thing we are doing here, that 2 times of this one. So, this matrix is a diagonal dominant matrix, and it has unique solution. So, I can solve this system, this is known to me, I can apply my Gauss-Seidel, Gauss-Jacobi, the iterative methods to find out this one, because this matrix is a diagonal dominant matrix. So, I know that for the iterative methods the diagonal dominancy was the sufficient condition. So, if I have applied the Gauss-Seidel or Gauss-Jacobi methods to find out the solution, then definitely we are going to get the solution, and the solution will be unique. So, based on this one we are able to find the cubic spline. So, that is the solution for the cubic spline. Once I get the value of this m0, m1, m2, all this value I will substitute in the given equation. So, here, so once I get the value of all mi's, I will put the values here, and then from here I will get the cubic spline. So, I can write that once we know the values of all mk's, k from 0, 1, 2 up to n, from equation 6 we can find the corresponding cubic spline. So, from the expression 6 I just substitute the values and I will get the hk is known to us, only thing that we need to find was mk. So, that is known to us now. So, I will substitute the value and get this cubic spline into place. So, this is the we will get the corresponding cubic spline function. So, this is all about that how we can express the cubic spline. So, we will stop today. So, today we have started with the expression of how to write the expression for the cubic spline, and then we have discussed that we get the matrix, and then how we can introduce the 2 extra condition to solve that matrix to find out the cubic spline for the given data. So, I hope you have enjoyed this lecture. So, thanks for watching this, thanks very much.